Welcome to this explainer. Today, we're stepping right onto the bleeding edge of modern engineering. We're going to explore a concept that honestly sounds like straight-up science fiction. We're talking about power generation pushed to its absolute limits, a place where the very boundaries between states of matter actually start to blur. So buckle up, because today, we are decoding the fluidized bed nuclear reactor.
Let's just dive right into this paradox. What if we could make solid nuclear fuel move like a boiling liquid? I mean, it sounds completely impossible, right? Solids are static, liquids flow. That's basic physics. But in the high-stakes realm of advanced energy production, overcoming this exact contradiction is actually the key to unlocking one of the world's most advanced nuclear technologies. And to be clear, we aren't talking about melting the fuel. That would be a massive, catastrophic failure. No, we're talking about something far more elegant here, a mechanical illusion that boosts safety and cooling efficiency to truly unprecedented levels.
To really grasp how this futuristic reactor works, we first have to wrap our heads around the fundamental physics at play here, this wondrous phenomenon of fluidization.
So what is fluidization? Basically, it's a physical process where granular solid material is converted into a dynamic, fluid-like state. The key word here is granular. We are not dealing with massive, heavy, solid metal fuel rods. Instead, we're dealing with tiny, individual particles. And when you subject these solid grains to the right physical conditions, they stop acting like a static pile of sand and start behaving entirely like a turbulent, flowing fluid. It's wild to think about.
Here's the exact sequence of how we actually achieve that state. Imagine this. First, you've got these solid particles resting calmly at the bottom of a containment vessel. Second, a gas is injected incredibly fast from beneath them. As that gas shoots upward, it hits the particles. Now, if the velocity of that gas is high enough, it literally overcomes the gravitational pull on those solid grains. And then, step 3, the particles lift. They separate and they begin to flow freely. They swirl, they mix, they bubble, literally exactly as if you were watching a pot of boiling water. It's just a mesmerizing feat of fluid mechanics.
So how do we take this fascinating trick of physics and use it to generate immense amounts of power? Let's take this concept and drop it directly into the heart of a modern nuclear energy facility.
In this specific design, the nuclear fuel itself is granular. Tiny particles of reactive material are placed inside the reactor core, and a coolant gas is just blasted up from below. Almost instantly, the nuclear fuel begins to fluidize. It dances and swirls in this constant chaotic motion. Now, why do this? Because every single individual particle is fully surrounded by that upward rushing coolant gas. The thermodynamic efficiency absolutely skyrockets. You're maximizing the surface area contact between the exceedingly hot nuclear fuel and the cooling gas that's carrying that heat away to generate electricity. It's incredibly efficient.
And that leads us straight to the secret of heat distribution. This design effectively solves one of the oldest and frankly most dangerous problems in all of nuclear engineering.
Let's put this into perspective. Traditional reactors rely on massive, static, solid fuel rods, with coolant just flowing past them. The major flaw there, you get uneven cooling. The absolute center of that rod gets vastly hotter than the outside, and that creates dangerous, localized hotspots that engineers constantly have to monitor and mitigate. But in a fluidized bed, because those fuel particles are continuously swirling and mixing together like a turbulent, boiling soup, the heat is distributed perfectly. You achieve a beautifully uniform temperature distribution across the entire reactor core. That means no hotspots and virtually no localized melting risks.
Now, this uniform temperature isn't just some neat parlor trick. It translates into massive, tangible engineering and safety advantages for the entire energy sector.
Think about the chain reaction of benefits here. The continuous dynamic movement of those fuel particles gives us extremely high heat transfer. That superior particle mixing guarantees the uniform temperature distribution we just talked about, and all of this culminates in significantly improved safety. Think about it. If a reactor is constantly self-mixing and thermally uniform, the mathematical probability of a catastrophic core meltdown just drops dramatically. It's this highly elegant passive safety feature that's quite literally built right into the physics of the reactor itself.
Okay, the theory is one thing, and reality is another. Let's ground ourselves for a second and look at the intense fluid mechanics challenges that are currently blocking the widespread global adoption of this design.
The engineering realities here are honestly pretty harsh. When you create a swirling tornado of hyper-hot, highly abrasive nuclear particles, you face severe thermal wall erosion. The inside of the reactor vessel essentially gets scoured and degraded by the constant physical impact of that fluidized fuel.
Plus, controlling that complex particle flow so it doesn't just get utterly out of hand, that requires incredibly complex, highly advanced design parameters. Trying to integrate a violently swirling, fluid-like core into strict, zero-tolerance nuclear safety systems is an engineering nightmare. It's a puzzle the world's brightest minds are still trying to fully piece together.
But despite those formidable challenges, researchers are absolutely not backing down. The potential payoff for humanity's sustainable energy future is just too immense to ignore.
In fact, the solutions to those brutal engineering hurdles are emerging right now. Researchers strongly believe that next-generation smart reactors equipped with hyper-fast AI monitoring systems are going to be the key. Artificial intelligence can actually predict and control the unbelievably complex flow of a fluidized bed in milliseconds, mitigating that wall erosion and optimizing the gas flow in real time. This pairing of AI and advanced fluidization is what's ultimately going to unlock these high-efficiency power plants for global sustainable use.
Ultimately, it all comes down to this incredible core synergy. When the chaotic dynamic rules of fluid mechanics meet the raw, staggering potential of nuclear energy, we don't just get some incremental improvement. We get entirely new technologies that can fundamentally reshape the world's power grid. We get a glimpse of a future where clean, limitless energy is far safer and more efficient than it has ever been before.
It really makes you wonder, doesn't it? What other impossible paradoxes are engineers quietly solving in laboratories right this very second? So are you ready to discover the greatest engineering marvels of tomorrow? If you want to keep exploring these advanced scientific wonders with us, make sure you're subscribed, keep questioning the impossible, and I will see you in the next explainer.